Good afternoon, everyone. I'm Mirela VASILE, and I'm working for the Belgian Nuclear Research Centrum in Mol. And today I will be talking about the test that we perform in order to use the AMP-PAN for cesium-137 determination in seawater samples. So what I will show you today is the context, why we are interested actually in using the AMP-PAN resin. I will shortly get over how we are performing now the cesium measurement in the seawater. So we are using the classical AMP coprecipitation method. Then I will present the results of the AMP-PAN resin, which are the conclusions of these tests and which are the perspectives. So shortly, the context of the study at SCK.CEN, our group, which is a low-level radioactivity measurement, it's responsible for radioactivity determination in different types of samples. So what we actually are responsible for is the monitoring of the radioactivity around nuclear installations in Belgium. So we do analysis of food samples, water samples. We do also bioassay analysis of the workers in the nuclear field. We do environmental samples, but we also are responsible for the monitoring of the North Sea. And one of the radionuclides which is requested by the regulatory body is cesium-137 in this type of water samples. All our techniques are actually accredited techniques according to ISO Guide 17025. How we are doing it right now in the lab? So it's really a lot of work, and we need a lot of waters to be brought into the lab. And we use the AMP powder to have a coprecipitation of cesium from this huge amount of water samples. We are using up to between 40 and 60 liters of waters, and AMP then is mixed with the sample, is leave it overnight for the coprecipitation, for the settling down of the precipitate, and then the sample is decanted, the precipitate is collected, is centrifuged, is dissolved, is again co-precipitation. So it's really a long procedure, and it's a time-consuming, complicated transport of such huge amount of waters into the lab, because we are analyzing different points within the North Sea water. So it's actually a laborious sample preparation, which it takes almost 1 week. And it's a full time for one of our technicians busy only with this. And this is one of the main reasons why we are looking towards to the AMP-PAN resin. But actually, what is this resin? It's an ammonium molybdophosphate, which is embedded in an organic matrix based on the polyacrylnitrile in order to improve its mechanical characteristics. So probably most of you are familiar with this AMP procedures, but this is resin is used for concentration and separation of cesium, and it has quite a good capacity for cesium. And the type of samples, like also Ode previously mentioned, that can be analyzed are acidified and maybe non-acidified seawater samples and liquid radioactive waste. But my talk or my test, our tests actually will be focused more on the seawater type samples. How do we use it in our laboratory? It's a very simple setup. So the only thing that you actually might need is a peristatic pump, which might need an investment. Because the rest, the sample and the waste containers are there. The AMP column, it's also. And an added value is you don't need the supervision once the procedure started. So you don't have to stay next to the pump to see how the flow rate is going. You check it at the beginning, and you can keep an eye once in a while to see if it's running smoothly. So our technician can do also something else in between. All our measurements are done using HP Germanium detectors, and they are calibrated for homogeneous samples. When the spectrum is analyzed using Gini 2000. And all our detectors, or most of them, are dedicated for the low active sample, so we need a very low background, which is actually achieved using a LED shield around the detectors. Which are the results from the AMP-PAN resin? So what did we do? We actually started with 2.4 liters of the seawater sample. We spiked it with cesium-137, and we acidified it with nitric acid with a pH below 2. But maybe before, to tell you why did we started with 2.4 liters is because we wanted to collect everything also after the resin and measure in a Marinelli beaker. So we measured the column itself, and we measured also the sample passed through the column. We initially wanted to establish a 2.5 liters per hour of flow rate, but by mistake it was set to 5 liters per hour. But still, even with, I will show you later that it was a good thing by mistake, let's say. In this graph, we can see the results of direct measurement of the column. So what we took the column and we placed it directly on the gamma detector. So what we could see actually is that we underestimate the results. So for the big columns, because I forgot to mention, we use two type of columns, 20 milliliter column and the 5 milliliter column. For the 20 milliliter column, we could see that the results are clearly underestimated, while for the 5 milliliter column, it's still slightly overestimated. And then what did we do? Because if we measured already the Marinelli beakers and we saw it's nothing going through the column, so everything should stay on the column. So we suspected that actually the sample is not homogeneous. And then we took the column and we did a vertical scan with a collimated HB detector. And we scan 3 positions along the cartridge. The upper side of the cartridge, the middle side, and the lower part of the cartridge. So we can clearly see that actually the count rate is going down while with the lowest count rate for the lower part of the column. So this is also clear that the distribution of cesium within the column, it's not homogeneous. So what did we do? Actually, we took the column and we transferred the resin in a measurement vial. And we tried to homogenize it a bit in the measurement vial. And then we could see that actually we get back a good agreement between the spiked value and the measured value in the transferred sample. And also we could see that we have good results independent of the particle size of the resin, and even with the flow rate of 5 liters per hour, which was by mistake set it, we have good results actually. For the non-acidified sample, because we only had one sample to see how the resin and how the sample is behaving using a non-acidified sample, we are still a bit underestimated, or we obtain lower results comparing with the acidified samples. Then we wanted to see is the acidification of the sample had really it's a big difference between the acidified and the non-acidified samples. But this time we used 14 liters of seawater like we would use in the routine analysis, and we spike it with 10 millibecquerels per liter. But please keep in mind that these are results for one sample per bar. So here in the graph, we can see for the 20 milliliter columns, the blue bars are the acidified samples, and we obtained really a recovery almost 100%, even with a high flow rate. But for the non-acidified samples, the recovery is almost 50%, which it means that it's either the flow rate, the cesium had not enough time to make the exchange and to be fixed in the column, or maybe it's another form that is not available for fixing on the column. So this has to be investigated a bit further before drawing a conclusion. For the 5 milliliter columns, for both of the samples, acidified and the non-acidified, we could see that the recovery was around 70%. So, but it was not a big difference between the acidified and the non-acidified samples. And this time we also used a flow rate of 2.5 liters per hour. So the flow rate was not very high, but still the recoveries were lower than for the 20 milliliters column. Then when we saw that the 20 milliliters are actually working very well, we tested with using the real sample. So what did we do? We took real samples from the North Sea, and we applied the both methods, the classical AMP and the AMP resin method. And this time we used the 20 milliliter column. We acidified the sample because we saw that we got very good recovery. And as you can see in this table, actually the time of the procedure using the classical AMP, it's almost 4 to 5 days, while with AMP resin, it's only 6 hours. The resulting samples, we measured them all over the weekend in order to have a low detection limit, and we could see that actually the results were in agreement. So both of them were, close to below the detection limit. Here I just wanted to point out a bit the influence of the sample, of the end resulting sample on the detection limits. So on the left side, we can see a pot, a vial, a measurement vial with a final sample resulting from the classical AMP. And on the right, we have the measurement vial after we transferred the AMP resin for measurement. So actually, here for the classical AMP, it's logical that once the distance between the source and detector is larger, we also can end up with a higher detection limit. While for the AMP resin, the source detector distance is shorter, and it's logical again that we have a lower detection limit with this. We also tested another sample. We had an EIA sample used for the intercomparison, and we used again two methods to compare the results. We used a 2.4 liter of sample, which was first measured directly on a gamma detector in a Marinelli beaker. And then the same sample, we actually acidify it and we pass it through the AMP resin using a flow rate of 2.5 liters per hour and using the 20 milliliter columns. So we can see actually that the results agree very well within each other. So which are actually the conclusions of the test that we perform is by using the AMP resin, we can have a faster and a much easier method. We can achieve few hours comparing with few days actually. For the 20 milliliter columns, we could see that we get very good recoveries, which are almost 100% recovery. For the 5 milliliter column, I think we still need to investigate a bit further to see how do they behave. We could also obtain good agreements between the AMP-PAN resin and the classical methods. And the perspective is that we want to implement this method actually in the routine analysis and to replace the classical method. But for this, we also need to validate, of course, the procedure at the end. And to do this, we need to decide on which type of column we are going to use at the end, the 20 milliliters or the 5 milliliters pre-packed columns, because these are more easy to handle. We have to investigate a bit more to see if it's really necessary to acidify the sample, because it will make the life much easier if not. And of course, we have to look into the reproducibility and repeatability of the results. Because at this point, if we have to transfer the resin into a measurement pot, I think maybe a weak point is that we have to look that every technician is doing in a reproducible way, that we can make sure that all the results are comparable. So if no acidification of the sample would be necessary, we will end up with no waste actually, because at this point, acidified water, we treat it as a chemical waste. And another improvement would be that maybe we can use it in situ treatment of the sample. So we can ask our colleagues from the Belgica that they can filter the sample through the column directly on the boat, and we can get finally only the column in the lab. So we don't have to deal with a large amount of seawater into the lab, and also the transport of such huge amounts of water. So I would like to thank you for your attention.